Alrighty, nerds. We're going to go ahead and tackle the last section of your logarithms chapter today. And originally I thought this was going to take 2 days, and then when I made the notes, I was like, oh, you know what? We got this. One day, we got this. And the nice thing about having the lesson done in 1 day is I have one more day that, I've all of a sudden made up. And my options were either move the test up to Tuesday, since I made up a day, or give you 3 days of review. I'm going to give you 3 days of review, and in those 3 days of review, I'm going to get you 2 different reviews. So that's what's going to happen with that. I will give you guys the first review tomorrow, the official test review, and we'll go from there, okay? But yeah, today all we're going to be doing is using logarithms to now solve the word problems that we did in Chapter 7. So we're going to be revisiting Chapter 7's financial style problems, talking about exponential growth and decay, continuous growth and decay, compound interest. We've sprinkled in a little bit of half-life stuff in there. Don't worry, you don't have to know how to write a half-life equation. You just have to know how to solve for pieces of it. But yeah, we're going to go ahead and get it crushed. So let's go ahead and start off with something we haven't really talked about before. I mean, I put it on the test, I put it on the last review, but we didn't really have a whole lot of practice with it, and that is continuous. You guys know that word means that you're going to better use E. Continuous decay. So how do we write a continuous decay model is the question. Well, if it was growth, it would have been A equals PE to the RT, but that's specifically for money. We did have it in our notes somewhere along the way, just the continuous exponential function, and it looks like this. Actually, let's do y equals. If it was growth, just a growth function, say you wanted to graph it, it would look like that. But if it's decay, it's a negative r. And that's the only difference between growth and decay for continuous, is positive r and negative r. The half-life of a radioactive substance is the time it takes for half of the atoms of the substance to disintegrate or, convert to a different substance. The radioactive substance thorium-230 is used to determine the age of corals. It has a half-life of 75,381 years. We're going to use a continuous decay model to solve for our decay factor, because that is this r. And you know what? I wrote r, but typically r is used for money and k is used for functions. They are the same thing, all right? Remember yesterday when I showed you guys the Newton's law of cooling? It had a k in it. Remember that? And I said that the k was the cooling or heating factor. This thing here that sits in front of the time or the variable x or whatever you want to put there represents your growth or decay factor if it's continuous, okay? So what do we know? We know that we will have half of our stuff left after this many years. We start with A. So if we start with A, how much is left when we have half of that? Think about yesterday's notes. The last question we did. 1/2 A, thank you, yeah. So if we're saying that we started with A, we're saying we ended with 1/2 A. Oh crap, 1/2 A, like that. And then we have E to the negative. We don't know K, but we do know T. 75,381. So we're trying to, crud, I said we know T, and then I wrote a T there. We're trying to solve for K, the decay factor. You would divide both sides by A, and as soon as you divided both sides by A, you would see that it cancels out. And that's why it actually doesn't matter what amount we started with. I'm trying to get K alone, but gosh dog it, it's sitting above an E. So how am I going to cancel the exponential base E? Natural log or log base E, they mean the same thing. Either way, we're going to use the ln of both sides. Like that. ln and e will cancel, and it gives me the ln of 1/2 equals this expression over here. So k is alone after you divide. And we'll grab our calculator for that one. We're probably going to have to get a lot of decimals on it. We'll see. Natural log of 1 divided by 2. Close up your argument. Remember, if you don't close your argument, the calculator doesn't know when your logarithm is finished. Divided by this negative 75381 equals, whoa, that is a lot of decimals. 1, 2, 3, 4, 5 zeros. And you know what? I'm just going to go ahead and write everything that's on my screen. You know what I could have done to avoid having to write out all of that? Yeah? Could have used scientific notation. I also could have just left it as a fraction. And you're looking at that going, ugh, but it's got a fraction inside the logarithm that's inside a fraction. And then there's this negative sign. And Michael, you're the one that talked to me about this yesterday. How could I address this situation? Do you remember what we talked about yesterday? It was your idea when we were solving that last question. Huh? Something about a fraction, yeah. If you flip the argument or the base over, it just puts a negative sign in front. But since this is already negative, I could say that k, if I decided to leave it as a fraction, I could say that k is the natural log of 2 divided by 75381. So if you don't want to write out all this, we could have just left this ugly thing for k in our equation. So you make a choice. Either you write out a whole bunch of decimals or you leave it as a fraction. And just to confirm to you that that is the same number, natural log of 2 divided by 75381. You'll see it's exactly the same number because flipping the argument over is the same as putting a negative sign on the front. And there was already a negative, so they canceled. Yes? Oh yeah, I mean scientific notation, there's no problem with it at all. The only thing I would be concerned with is you would have something with an exponent inside your exponent. That's the only thing that would concern me, that you might handle that incorrectly. But it can definitely be done though. I'll leave that up to you. So it says, use this model to determine how much of a 5-gram sample of thorium-230 would remain after 2,000 years. So we have to write our model. Y equals 5 e to the negative, and like I said, we can either write this decimal or we could write this fraction. Which one do you guys prefer? Oh, she said the fraction very loudly before anybody else spoke, so that's what we'll do. There. So what do we have to do? We have to figure out how much is left after 2,000 years. That's t equals 2,000. We just have to plug in t equals 2,000. And this is a multiplication. So I would strongly suggest that you do this in pieces and parts if you are using the battery operated calculator. And if you're using the nice solar calculator, you're going to need to be a master of parentheses. Or do it in parts. Completely up to you. Someone says parentheses. They'd rather be a master of the parentheses. Alrighty. Let's see about these parentheses skills that I have been honing since freshman year of high school. 5 second ln gets me my e. All right. E opened up its own set of parentheses. The calculator is asking me what all is in the exponent of this e. And here's what I tell it. I want the negative ln of 2. ln opened its own set of parentheses. I just closed the natural log. Divide that by 75381. Multiply by my value for t, which was 2,000. And that was everything in my exponent, so I now close the exponent. And I hit equals. And I have my answer. Haven't lost a whole lot. But that's because 2,000 years really isn't much when you talk about the length of time the half-life is. The half-life is over 75,000 years. So what did we do? We did this. That's what we did. And let's round this to 2 decimals, about 4.91. I wonder if I meant for that to be 20,000 instead of 2,000, if I missed a 0. Because if we had done 20,000, we would have noticed a lot more was gone. Out of curiosity. Let me go up here, scroll all the way over to my 2,000, tack another 0 on. Still not much difference, is it? That half-life of 75,000 years doesn't mess around. Whatever. There it is. So talk to me about it before we go anywhere. What can I help you with? What kind of questions can I answer? If you had chosen to write this to 2 decimals, we would have gotten the same answer. It wouldn't have mattered. I mean, this is more exact, but... Yes? So why is the fraction negative? All right, so for here, what we were doing was we were solving for k. But the equation already has a minus in front of it because it is decay. So we would have expected our k value to be a positive number because negative was part of the equation. That's why. So once we solved for k, when we plug it back into the formula, it comes after this negative symbol. That's why. And if we didn't have a negative sign there, that'd be exponential growth instead of decay. Okay? Okay. Yes? Is there going to be a half-life question on the test? I don't see a reason why not. It would either say continuous or wouldn't. You already know this formula. It's from chapter 7. Alrighty. Let's do another continuous decay because clearly that spooked some people. Radioactive carbon-14, our good old buddy carbon-14, has a half-life of 5,730 years and a known decay factor of 0.00012. Remember that bowl that we had from our archaeological dig site the other day? It's coming back. When archaeologists sampled a clay bowl found at a dig site, it contained 17.2% as much carbon-14 as it would have originally contained. We want to use a continuous decay model to determine the age of the bowl to the nearest year. What do we know? We know K. We don't know A. We don't know Y, so to speak, these two things. But what we do know is that there's 17.2% remaining. Yes? K is the growth or decay factor. It's basically the rate if we were talking money. So one of the other things that I told you could do with these ones where you're not told how much you start and end with, I told you that you could make up a number to begin with if it helps you. If you would rather do that than do it this way, then make up a number. That's fine. It's not a big deal. Let's go ahead and do this one that way. Yes, Gracie? For part A of this one, you keep getting 5 point. Part B? I'll pause the video while I check your calculator. More than likely, you're just missing a parenthesis. So we figured out what was wrong with Gracie's method on her calculator, but Someone has asked me how to do it on this calculator, so I figured it should make it into the video because some people are not going to let go of this antiquated piece of calculator. So for this calculator, what you have to do is you have to follow the order of operations for it. So you have to type everything backwards. So I'm going to start with 2 natural log. I'm going to divide that by negative 75381. 75381 negative sign equals. I'm going to multiply that by 2000 equals E, so second ln, times 5. Everything's backwards. And there you go. Whee! You're welcome. Okay. Oh, God. Another calculator problem. All right, bring me your calculator. Syntax error. Syntax error means that you're typing a minus sign instead of a negative symbol. Well, what? Clear. Okay. Are you using this symbol? There you go. Holy crap. All right, moving on. So we're back to this question. I was probably 3 million calculators and other distractions. What we're going to do for this one is we're going to make up a starting amount because, yes, you can make it 1 if you would like to, sure. So if we want to make the starting amount 1, then what is the ending amount? Well, it's 17.2% of 1. What is 17.2% of 1? 0.172. We're on the second question. Yeah. We're 16 minutes into this video. We're making up a starting amount. We're calling it 1. And we're saying if we have 17.2% of that remaining. This is the other way of doing it instead of saying A and 0.172A. It's just the other way of doing it. Just like I did yesterday. Showed you both ways. Anyway, we're going to plug these into our equation. We know that we will have 0.172 of our original 1 remaining. And that's going to happen with a known decay value of this number. So negative 0.00012, but we don't know the time and we are solving for the time. Look, dividing by 1 is not going to change anything, which is why we said let the starting amount equal 1. That makes life very easy. And we're just trying to get t alone. So just like the last question, you're going to use the common log because the common log cancels natural base e. ln, excuse me. Natural log, sorry. And we'll cancel here. And what that gets me is the natural log of 0.172 equals this thing. And all we have to do is divide by that nasty decimal to solve for t. It says round to the nearest whole year. Let's see what we get. Natural log of 0.172 divided by negative 0.00012 equals, whew, nearest whole year, 14669. Over 14,000 years. That's an old bull. So when you don't have a starting amount, feel free to make one up. And I would say either say you started with 1 or say you started with 100. Those would be the two easy ones, if that's how you want to do it. When we first started chapter 7, And that's not a mistake. I meant to say that. When we first started chapter 7, we did a lot of exponential growth and decay problems that involved 1 plus r for growth and 1 minus r for decay. But these formulas were used when it was a one time per unit of time type of thing. So a one time per day situation, and then you tracked it for some days. Or a one time per 20 minutes, and you tracked it for a number of 20-minute periods. Or one time per year. The point is, these formulas were used for one time per unit of measure. You purchase a new car for $28,000. And we had a question just like this. I literally copied and pasted from the old notes, and I changed it from how much would it be worth to how long would it take until it was worth. That's all I did. So you purchase a new car for $28,000. Unfortunately, the value of your car depreciates, which means it goes down by about 8% per year. How long will it take for your car to drop down to $10,000? And we're going to round to 2 decimals. Depreciates. So we're ending with 10,000. Started with 28,000. 1 minus 8% or 0.08 raised to the t. And we're just trying to get t all alone. I'm just going to subtract real quick. 1 minus 0.08 is 0.92. Okay, we did a bunch of these kinds of things yesterday. It's no longer a word problem. Now it's just a solve for t problem. What do we do first? Divide. So first thing you're going to do is divide by 28,000 on both sides. I don't know if that's going to be a pretty fraction or not. So you know what I'm going to do? I'm going to leave it as a fraction. I mean, if you wanted to reduce it, you could. All the zeros come off. That's 5 over 14. If you really wanted to. But even that is thinking that you don't have to do when we're letting the calculator do the heavy lifting. So I'm not even going to bother. And since we're going to have to type this on our scientific calculator, we don't want to use log base 0.92 because we don't have a way of typing that without change of base. And if you're going to have to use change of base, you might as well not bother using log base 0.92 and go straight to either the common log or the natural log like we did over the last 2 days. It doesn't matter which one you choose. They're both going to work equally. But, you know, I typically reserve the common log for integer style things, number style, and that's not integer, but like standard number things. And I use the natural log basically for e. So if it's not e, I typically don't use natural log. I could, I just typically don't. So I'm going to go ahead and find the common log of both sides. Because, just like it did in the previous examples, well, at least from yesterday, I have an exponent in my argument. I can use my expanding rules to move this t down to the front. We'll switch colors, that way it's obviously different. And I'm going to have log of this fraction and I'm bringing the t down to the front, and then I have log of this decimal. T is alone now when we divide. And then we'll grab our calculator and we'll just make sure that we know how to use our technology appropriately. This is rounded 2 decimals. So I'm typing this. Log of, and then I got a fraction. Close up that argument. Divided by log of this decimal. Close up that argument, and I hit equals. Boink! About 12.35 years. So I would like to know what I can help you better understand if you have questions about this. Yes, sir. Yes. Mm-hmm. You can't do that because that's the half-life time. That's because for this one I didn't know K. I had to use the length of the half-life. It was a time that brought A down to half of its original amount. It's just what was given to you. No, because if you use the half-life, then that's going to get you down to half of what you started with. That's the idea. Every time, if you use time equals 5,730 right there, you're going to get 1/2 over here. Guaranteed.
What if I was to multiply 5,730 by 2?
Why would you multiply it by 2? You can't just multiply something by 2. No, it doesn't work like that. That's not how exponentials work. For this one, I gave you K. The length of the half-life just tells you how long it would have taken you to get half of it gone. But that's how you solve for this number. If no, it's not how it works. Like if I did this, so this is how I would solve for K, right? I'd have to take the natural log of both sides and then divide by that number. Okay. This is a truth. After this much time, I have half left over. So I take the natural log of both sides. There's the natural log of the left. Then divide by this negative number. The K value that was given to you. Okay? So if it wasn't given to you, that's how you would have solved for it, which is what we had to do up here. All right. On to the back. More savings accounts. You deposit money into a savings account that grows at a rate of 2.5% per year. Look at that. Per year. So that means we're dealing with this equation. We want to know how long it would take for your money to double. Again, you weren't given a starting amount. So what amount would you like to say you started with? 1. That makes life really easy. So if you start with 1, you're ending with 2 because it's doubling. So we can go directly to this formula. 2 equals 1 plus, we've already divided by 1 because that means nothing, the 0.025 to the t. And we just have to solve for t. Look how easy that is. It's so much less work than actually having a starting and ending amount. So you go, okay, 2 is 1.025 raised to the t. We're going to have to use the common log if we use log base 1.025, so you might as well just use the common log to solve for it anyway. Because if we just go ahead and use the common log to solve, we're not even using the change of base. So let's just say common log of both sides. That t will get to drop down to the front. Bless you. And I hope you can see, all you have to do is divide. And we're finished with this question. They're remarkably fast questions. Let's see, with that measly 2.5% interest, how long it would take to double. We're going to round to 2 decimals. Log of 2 divided by log of, I forgot to write the word log here, sorry. There you go. 1.025. Close it up. And it's going to take over 28 years. 28.07 years. Wowza. Remember, we started with 1, we ended with 2. P stands for principal, which means beginning amount. Alrighty, so we've had some with E in them. We've had some that were just once per year style growth or decay. How about multiple times per year? Compound interest. You deposit $1,700 into a savings account that pays 1.8% annual interest compounded quarterly. The moment you see that you have the word compounded and it doesn't say continuously, you know you're using this formula. Where N stands for the number of compounds per year. How long will it take for the account to have $5,000? We'll round to 2 decimals. Okay, let's fill it out. We know we're ending with 5,000. We began with the 1,700. 1 plus our rate as a decimal, meaning not a percent, would be 0.018 divided by N, where N is the number of compounds per year. So if it says quarterly, how many is that? 4. 4 quarters in $1. And then we have 4 times T, and we're solving for T. All right. I wonder if that's pretty enough for me to write it down. 1 plus 0.018 divided by 4 is, yes. So we'll just write that as 1.0045. There. Just like all the other ones, when we have that number sitting on the front, the very first thing that you're going to want to do is divide by it. So we're going to divide by 1,700. Now, I doubt 5,000 over 1,700 is pretty, just to prove a point. Ew! So since it's not pretty, I'm going to leave it as that fraction. Now, if you want to, you could say it's 50 over 17, just so you're writing or typing less. But again, we're trying not to think very much, right? So let's just leave it as that fraction. We'll let the calculator do all the heavy lifting for us. Oops, that's supposed to be a 0. There we go. T is hiding up there in the argument position, or in the exponent position, excuse me. But if it was in the argument, we could drop it down to the front. So, either natural log or common log, it doesn't matter, it's completely up to you. Again, I typically reserve the natural log for times when I'm dealing with E. There's no E here. So I'm going to choose to use the common log of both sides. Like so. Now 4t is an exponent in the argument. So I can use my expanding rules and bring it to the front of that logarithm. I'm running out of vertical space over here. So I'll just go over here. Log of this fraction, which was not pretty, and that's why we're leaving it like that. The 4t comes to the front, and there is still a log of 1.0045. And we're trying to get t all alone. But since that's all multiplication, I say we get 2 alone in one step. Not 2, t. Let's get t alone in one step. Instead of doing 2 divisions, let's just divide by 4 log of 1.0045. And you know what I'm going to do? You're going to put parentheses around that when you type it on your calculator. That way the calculator understands that there's a multiplication in the denominator of that fraction. If you don't use parentheses when you type this, it's going to do this log divided by 4. It'll get a number for that, and then it will multiply your answer by this log. That's not what you want. You want it to divide by it. So let's see. The 4's cancel, the logs cancel, and it gets me t equals log of 5, 1, 2, 3, divided by 1700. I'm closing the argument. Divided by. I can see that there's multiple objects in this denominator, so I'm going to tell the calculator, yo, my denominator starts here. 4 times, not 5. 4 times log of. Okay, log open its own parentheses. 1.0045. That finishes the logarithm. That finishes the denominator. That finishes the question. 60.07 years. $60 years to go from 1700 to 5000. Man, that's slow. And it's still so much faster than what the current rates are in the banks. And then we have one more. And we'll call this chapter a wrap. Continuously compounding money. PERT. And it's growth. You deposit $6,000 in an account, that's P. Continuously compounded interest, that's why it says E. After 8 years, there's T. Your account has this much money in it, that's A. It says, what is the interest rate? Rounded to 1 decimal. Let's fill out what we know. 7328.42 equals 6000. E to the 8R. See, we didn't know R this time. We solved for it the same way, though. It really doesn't matter, but specifically, we didn't know R. And why does this one matter? Because I want the interest rate as a percent. So it's going to have one more step on it. Just like all the other questions, though, you're going to start the same way. You're going to divide. That's not going to be pretty. So leaving it in a fraction is going to be your best bet. That way you're not thinking about it. Just let the calculator deal with it. And I said it a whole bunch of times, but I'm trying to cancel this E, so now I can pull ln out of my back pocket and go, all right, E, time to get canceled. Boom. So the natural log of this fraction equals 8R. All you have to do is divide by 8. Natural log 7328.42 divided by 6,000. Close the argument. Equals. Divided by 8 equals. That is 0.025, which is 2.5%. Awesome.